Let's take a look at what a professional soil analysis of this particular soil looks like. Right here, I have a soil analysis of this particular clay soil that was done at Midwest Laboratories. We will start with organic matter. In this particular sample, we have an organic matter content of 0.8%, which is very low. In this type of soil, we ideally should have between 5 and 10% organic matter content to make it suitable for gardening. Then we move on to phosphorus. There are two different types of phosphorus test. One is called the weak braid test, and the other is the strong braid test. They use different testing methods, but either way, with this clay soil, we can see that the phosphorus levels are very high for both the weak and the strong braid test. The ideal level should be around 40 parts per million. However, in this sample, we have 90 parts per million in the weak braid test and 126 parts per million in the strong braid test, which is extremely high. When phosphorus levels become too high, they can actually turn toxic for plants and prevent other mineral nutrients from being properly absorbed. Moving on to potassium. We have a level of 160 parts per million, which is close to normal. Ideally, the maximum should be around 150 parts per million. But because everything else in this soil is out of balance, this level is considered high. Moving on, we have magnesium. In this clay soil, the magnesium level is 502 parts per million, when it should be around 200 parts per million. Magnesium is one of those minerals that can make the soil very tight, hard, and extremely dense. For whatever reason, a high magnesium level tends to create highly compacted soils. Then we move on to calcium. Although 1,413 parts per million might seem like a high number, ideally it should be at least at 2,000 parts per million. Calcium is beneficial for the soil because it helps makes it a little softer and also supports the living organisms in the soil. Next, we have sodium. Sodium in high amounts can be toxic not only to plants, but even to humans. In this sample, the sodium level is 138 parts per million, when the maximum should be around 50 parts per million. So it's almost 3 times higher than it should be. That's one of the reasons plants do not perform very well in this kind of excess. Mythically, it is said that the Roman army salted their enemies' fields, which is untruth, as salt was part of their payment or salary. The term salting the earth is a symbolic gesture, occasionally referenced in Eastern biblical texts, including the Old Testament, to illustrate God's power and the toxicity of salt in excess. When we look at the soil pH or potential hydrogen, we can see that it's at 7.4. A pH of 7.4 means the soil is alkaline. As we can see, it's fairly alkaline, and plant tends to struggle in alkaline soils because many nutrients become locked out and unavailable to them. So plants cannot absorb those nutrients. Moving on to the buffer index. The buffer index is what indicates the stability of the soil pH. It basically means the soil has enough reserves to absorb changes without the pH changing too quickly. A simple way to understand buffer index is to think of it like a bank account. If you have $10,000 at the bank and suddenly you get sick and you need to pay $5,000 to the hospital, it affects you, but you're still okay because you still have money left. But if you only have $5 in your bank account and suddenly you need to pay $5,000 to the hospital, then you have to borrow money and go into debt. The same thing happens with the soil. When the soil has little or no buffer index, like in this case, the pH can suddenly drop very low or rise very high because there is nothing there to stabilize it. The cation exchange capacity, or CEC, is the ability of the soil and its minerals to hold and exchange electrical charge nutrients. Plants absorb nutrients primarily as ions dissolve in water, meaning nutrients are taken up either as cations, that's positively charged ions, or anions, negatively charged ions, depending on the element. In this case, we have a value of 12.3, which is pretty good. This soil has lots of extremely small clay particles that carry a negative charge, and that means it has a good ability to hold and release positively charged nutrients. Soils with high cation exchange capacity, or CEC, hold fertilizers very well, while sandy soils with low CEC lose nutrients quickly. Quick note: clay soils are very greedy. While they do attract and hold positively charged nutrients, they don't release them very easily because soil compaction, poor drainage, high pH, plus plant roots are not able to easily penetrate clay soils. When we get to the soil-based saturation percentages, we can see that some elements are in excess. Potassium might still be within acceptable range, but magnesium is extremely high, and sodium is also very high. These two elements, sodium and magnesium, are the main ones that make the soil become very hard, tight, and compacted. In excess, they can also become toxic to plants. The soil-based saturation analysis helps us determine the proportion of soil nutrients like calcium, magnesium, potassium, and sodium relative to acidic elements like hydrogen. It is important to keep them in balance so one does not interfere with the other ones. Aluminum toxicity only becomes a problem in highly acidic soils below a pH of 5.5, where the aluminum becomes soluble and causes phytotoxicity, that is, stunted root growth, poor nutrient uptake, and tissue death. As for hydrogen, because the soil is so alkaline, there is very little hydrogen present. A high pH or potential hydrogen means that the soil has a high potential to absorb hydrogen, but is lacking hydrogen. A low soil pH means the soil has already absorbed lots of hydrogen. If we were to measure the pH of pure sulfuric acid, it will be 0 because it cannot absorb or dissolve any more hydrogen. Quick note: I have been told that I have a very high PW, or potential wealth. In the meantime, I'm still broke. Nitrogen. We only have 2 parts per million of nitrogen, when ideally it should be between 10 to 15 parts per million. Lack of nitrogen shows as yellow leaf in most plants. Then we move down to sulfur. Sulfur is beneficial for plants because it helps with many important plant functions. In this case, we have 9 parts per million, which is fairly low. Next, we move on to zinc. which is another important micronutrient. Here we have 1.2 parts per million, and ideally it should be between 1 to 3 parts per million to maintain a good balance. Manganese. Don't confuse it with magnesium. Manganese is another important micronutrient. Ideally, we should have between 10 and 25 parts per million. But in this case, we only have 2 parts per million, which is very low. The next one is iron. Iron is at 24 parts per million. A good range is between 10 and 50 parts per million, but alkaline soils block iron from plants. Copper. Copper is at 0.8 parts per million, when ideally it should be between 1 and 3 parts per million. Copper is another one of those micronutrients that plants need in small amounts in order to properly carry out their functions. Next, we have boron. In this sample, we have 0.4 parts per million, when it should be between 0.5 and 1 parts per million. So we're below the ideal range. Then we have the excess line rate. Since this soil is low in calcium, it has a low excess lime rating. Having a low excess lime rating is good because lime raises soil pH and blocks nutrients from the plants. The same goes for soluble salts. When we talk about soluble salts, we're not necessarily talking about sodium. Soluble salts are done by the reaction between an acid and an alkali compound. Even fertilizers are considered salts, and they are the main cause of soil contamination. Besides all this testing, it is a good idea to get to know your soils very well. In my case, what I do is I collect buckets of soils from most places I work and bring them home, where I can keep testing and see how they react under different wetness conditions. See how the pH changes, the type of gases or smells they produce, and the microbial activity under those conditions.